Welcome back to the deep dive. Today, we are opening up a file that, I'll be honest, looks incredibly intimidating at first glance. We're talking about iterative methods for large, sparse, linear systems.
Yeah, it's a title only a mother could love, or, a mathematician.
Exactly. But as I was digging into the sources you sent over, I realized this isn't really a story about dry formulas. It's a story about hitting a wall, a huge wall. It's about what happens when the problems we want to solve get so big that, well, standard math just breaks.
That's a great way to put it. This is really a story about solving the impossible.
So let's set the scene for everyone listening. We all remember algebra class, right? You get a system of linear equations, something like x plus y equals 10, x minus y equals 2. You solve for x, you substitute, you find y, it's clean.
Right, it's precise.
Yeah.
That's what we call a direct method.
Mm.
And in high school, or even first-year college stuff, that works perfectly. But what we're talking about today is a completely different beast.
We're not talking two variables.
Not even close. We're talking about n variables. And n is, say, a million. Or 10 million, sometimes a billion.
A billion variables. Wow.
Easily. I mean, think about simulating the airflow over a jet wing to check for turbulence, or modeling an entire continent's electrical grid. You end up with these systems where n is just massive.
And the outline calls this the impossible problem. So why can't we just use that high school method? Just throw a supercomputer at it.
To get why, you have to visualize the data. These systems are what we call sparse. So imagine a giant spreadsheet, a million rows by a million columns.
Okay, that's a trillion cells, a huge spreadsheet.
Right. But here's the kicker. Almost all of those cells are zero. They're empty. In physics, things usually only interact with their immediate neighbors. An air molecule pushes on the one next to it, not one a mile away.
So the matrix is mostly empty space. Intuitively, you'd think, great, zeros mean less work.
You would think that. But if you try to use that classic method, Gaussian elimination, you trigger a complete disaster. It's called fill-in.
The curse of fill-in. That sounds ominous.
It's a nightmare, a total nightmare for computer scientists. When you start manipulating the rows, like adding row A to row B to cancel a variable, you mathematically destroy those zeros. You turn them into non-zero numbers.
So you're polluting all that empty space.
Exactly. It spreads like a virus. Suddenly, this matrix that fit into memory because it was mostly empty, it's not empty anymore. The memory usage just explodes. We're talking cubic growth, what we call O of n cubed.
So let's put that in perspective. A million variables.
You'd need exabytes of RAM. I mean, more memory than exists on every computer on Earth combined. It is physically impossible. You cannot store the steps needed to get the exact answer.
Direct solving is just.
Yeah.
It's off the table completely. And that forces this huge shift in thinking, the paradigm shift.
Right. If we can't factor the matrix because it destroys the zeros, we have to leave it alone. We have to treat it as this fixed thing, an operator. We don't touch it.
So if you can't calculate the answer directly, what do? Just guess.
Essentially, yeah. You guess. That's the whole iterative paradigm. We start with a guess. Let's call it x0. We run it through the math, see how wrong we are, and then use that error to make a better guess, x1.
And you just keep doing that over and over.
Over and over and over. You generate a sequence of guesses that hopefully converges to the true solution.
It feels like a philosophical change. We're moving from exactness to good enough.
We are. But here's the thing. In engineering, you don't actually need the answer to the billionth decimal place. You need an answer that's within a certain tolerance. If the error is so small that the bridge won't fall down, you stop. You declare victory.
Okay, so let's unpack the toolkit. How do we make these guesses smart? The sources start with what they call stationary methods. These feel like the ancestors of all this.
They are. They're the foundations. They go back to the 19th century. The core idea is called splitting. You have this hard matrix A you can't solve. So you split it into two parts, M and N.
M and N. Very creative.
Mathematicians, were very literal. You make M something really, really simple to solve, like just the diagonal of the matrix. And you shove all the hard, complicated bits into N. Then you just solve that simpler M system again and again.
And this gives us the two classic flavors, Jacobi and Gauss-Seidel. I love how they're always presented together, like a rivalry.
They're the Coke and Pepsi of early linear algebra, absolutely.
Okay, so what's the difference? How does Jacobi play the guessing game?
Think of Jacobi as a very synchronized process. Imagine all your variables are students taking a test. In Jacobi, to get their new answer, everyone is only allowed to look at the answers from the previous round.
So it's like taking a snapshot of the whole system, and everyone updates based on that old snapshot all at once.
Exactly. And because everyone's looking at the past, they don't depend on each other's current work. You can calculate all million updates at the same time. It's incredibly safe and really easy to parallelize on a modern computer.
But there's a but.
But information travels so slowly. If variable A changes, variable B sees it in the next step. But variable C, which is connected to B, won't feel that influence for 2 steps. The news just propagates across the grid at a crawl.
So it's slow to converge. Which brings us to its rival, Gauss-Seidel.
Right, Gauss-Seidel is impatient. It says, look, I just calculated a new, better value for variable A. Why wait? It uses that new information immediately to calculate variable B in the very same step.
Ah, so it doesn't wait for the snapshot. It's always using the freshest data it has.
Correct. And because that information travels faster, it typically converges much more quickly than Jacobi does.
That sounds just better. What's the catch?
The catch is you lose all that lovely parallelism. Variable B is now waiting for variable A to finish. You can't do them at the same time anymore. You've created a dependency. You're sequential.
A trade-off. Convergence speed versus computation speed.
Exactly. But then people got clever. They looked at Gauss-Seidel and thought, we can tune this. Which leads to one of my favorite acronyms, SOR.
Successive over-relaxation. It sounds like a spa treatment.
It is definitely not relaxing for the computer. SOR takes the Gauss-Seidel idea and just adds a turbo boost. It looks at the direction the solution is moving and asks, well, if we're heading that way, why don't we just go even further?
The sources used an analogy of rolling a ball into a hole.
It's a great visual. Standard Gauss-Seidel is like letting gravity pull the ball toward the hole, as far as like running up behind the ball and giving it a kick in that direction.
And the size of that kick is this parameter, omega.
Right. If omega's 1, you're just doing normal Gauss-Seidel. But if you set omega higher, like say 1.5 or 1.9, you're over-relaxing, you're extrapolating. You're basically predicting where the answer is going to be and trying to jump ahead.
And that speeds things up significantly.
Yeah, it can cut the computation time in half or even more, but you have to be careful.
Why is that?
Well, imagine kicking that ball too hard. It just rolls right over the hole and out the other side. If you set omega too high, usually 2 or more, the whole method becomes unstable. The numbers just blow up.
So it's a balancing act, speed versus crashing.
Precisely.
Okay, so those are the stationary methods, the classics. But the outline shifts gears here to what it calls the modern standard, the powerhouse, Krylov subspace methods.
This is where we leave the 19th century and really enter the space age. Stationary methods are linear. They do the same simple thing every single step. Krylov methods are adaptive.
Adaptive. I like the
Yeah.
sound of that. How does it work?
Instead of just updating based on the very last step, Krylov's methods build a search space. They use the history of the errors, they remember where they've been, and they use that to build a map of the problem as they solve it.
And the king of this hill seems to be a conjugate gradient, or CG.
CG is the gold standard. It's elegant, it's fast, it's beautiful math. And it's a really big set, but it only works for a specific type of problem.
Here come the terms symmetric, positive, definite.
It sounds scary, but really it just means the matrix is nicely balanced. Symmetric means if you flip it across the diagonal, it looks the same. And positive definite means it has this nice bowl shape, not a saddle. A lot of physics problems like instructional mechanics or heat transfer have this property.
And if you have that structure, what makes CG so good?
It minimizes something called the energy norm of the error. It guarantees that every single step takes you closer to the solution in the most optimal way possible. It never backtracks. And it has what we call superlinear convergence.
Which means?
It starts off kind of slow, but as it learns about the matrix, it accelerates, gets smarter as it goes.
That sounds perfect. But the real world is messy. The sources have a section called the tail of the tape, which implies a fight. What if the matrix isn't symmetric?
Then CG it breaks. You can't use it. You have to enter the ring with the general solvers. And there are 2 main contenders here, GMRES and Big G stab.
All right, let's break them down. In the red corner, GMRES.
GMRES stands for Generalized Minimal Residual. Think of this one as the tank. It is robust. It's mathematically guaranteed to reduce the error, the residual, every single step. It will strictly march down the hill to the solution.
That sounds great. Why would you ever use anything else?
Because the tank is heavy. To guarantee that descent, GRES has to remember every single direction it has ever taken. It stores all these old vectors.
So the longer you run it?
The more memory it eats. The memory usage grows linearly with every iteration. And eventually you run out of RAM and the computer crashes.
So that's the fix. You just reboot the tank.
Basically, yeah, it's called restarting. You tell it, okay, wipe your memory, forget history, and start again from here. It saves memory, but deleting that history, it really hurts the convergence speed. It slows down.
Okay, so that's the tank. In the blue corner, we have BiCG stab.
Biconjugate gradient stabilized. We can just call it the speedster.
Mm-hmm.
It doesn't store that long history. It uses a constant, very low amount of memory, just a few vectors. It's super fast per step.
But looking at the graphs in the source material, the convergence for GMRES is this smooth, beautiful curve going down. The line for BiCG stab looks like a seismograph during an earthquake.
It's wildly irregular. The error will spike up, then down, then way up, then down again. It's a chaotic ride. It usually gets to the solution, and often faster than GMRES, but there's just no guarantee of smoothness along the way.
So you're choosing your poison: high memory with smooth progress, or low memory with a chaotic ride.
That is the daily struggle of a numerical analyst, yes.
Now, I want to pivot to a method that stood out to me because it feels retro. The Chebyshev iteration. The sources call it the specialist. Why would anyone use this old school method that uses fixed polynomials when we have smart adaptive things like CG?
This is where we connect to the cutting edge of supercomputing hardware. The big weakness of those smart methods like CG is that they need to make a global decision at every step.
How so?
Well, to decide the next optimal direction, CG has to calculate a dot product. And that means summing up numbers from every single variable across the entire system.
And if you're running this on a supercomputer with, say, 10,000 graphics cards,
They all have to talk to each other. They all have to stop what they're doing,
Yeah.
sync up, share their numbers, agree on the sum, and only then can they move on. It's a massive red light at every single intersection. We call it a global reduction.
a traffic jam.
A global traffic jam. It completely destroys performance on these massive machines. And this is where Chebyshev comes back into style. Chebyshev is, well, it's dumb in a very clever way. It doesn't adapt. It follows a preset path.
So it doesn't need to stop and ask for directions.
Exactly. It only ever looks at its immediate neighbors.
Yeah.
It never has to stop and ask the whole group for a consensus. It just flows.
So on a massive scale, the dumb method is faster because it's not clogging up the phone lines.
It hides latency. But, and this is a huge Beinheim food, but because it's not adapting, you have to tell it exactly where the boundaries of the problem are. You need to know the eigenvalues, the min and max bounds of the matrix before you even start.
And if you get those bounds wrong,
It explodes. It diverges instantly. So it's very high risk, high reward.
okay, so we've got our solvers, the tank, the speedster, the specialist. But the sources make a very strong claim here. A solver without a preconditioner is rarely effective.
That is rule number one of sparse linear algebra. You almost never use these solvers naked.
Let's unpack preconditioning. The analogy in the text is flattening the terrain.
It's a great one. Imagine you're trying to find the lowest point in a landscape. That's your solution. If the problem is ill-conditioned, that landscape is a nightmare. Deep, narrow canyons, jagged peaks. If you drop a ball or solver into that, it just bounces back and forth between the canyon walls.
Right.
It takes forever to get to the bottom. Preconditioning mathematically transforms that landscape. We multiply the system by some matrix, M inverse, and ideally, this turns those narrow canyons into a smooth, round bowl. You drop the ball, and it just rolls straight to the center.
That sounds amazing, but doesn't finding that magic matrix M take a lot of work? I mean, if M is perfect, isn't that just solving the original problem?
That's the catch. If M is the perfect inverse of A, we're right back to the impossible problem. So we need an M that is just good enough. We want something that's cheap to calculate, but effective enough to smooth out the worst of the bumps.
What are the go-to options for that?
The most popular workhorse is called ILU, incomplete LU factorization. Remember how we said Gaussian elimination fails because of fill-in?
Right, the memory explosion?
ILU basically says, okay, let's do the elimination, but whenever we create a new non-zero entry that's really small, let's just throw it away, just pretend it's zero.
So you're intentionally doing the math wrong.
We're doing the factorization approximately. It keeps the matrix sparse, it saves the memory, but it gives us a landscape that is mostly smooth. And that's usually enough to let GMRES or BCG scab finish the job quickly.
Incredible. It's all about managing approximations.
Okay, before we wrap, we have to touch on what the outline calls the boss level, multi-grid and domain decomposition.
These are the heavy hitters, yeah. If you're simulating global weather or modeling nuclear fusion, you are using these methods. Let's start with multigrid. The key insight seems to be about different frequencies of error.
Yes, think about a blurry photo. You have high frequency noise like static or graininess and low frequency error, like the whole left side of the picture being too dark.
Okay, got it.
Your standard solvers, like Jacobi, are actually great at smoothing out the static, the local pixel-to-pixel noise, but they are terrible at fixing that big, global, too dark problem.
So multigrid uses a hierarchy to fix this.
It does something brilliant.
Yeah.
It solves the problem on the fine grid to clean up the noise. Then it shrinks the whole problem down to a coarser grid, fewer points.
Why shrink it?
Because on that coarse grid, that big, slow global error now looks like local noise. The solver can fix it easily there. It keeps shrinking down until the problem is tiny, solves that, and then projects the answer back up through the levels.
It's attacking the error at every scale, all at once.
And because of that, it achieves the holy grail. O of n complexity. You double the problem size, you only double the time, it scales perfectly.
Then, just briefly, what about domain decomposition? Divide by space.
This one is super intuitive. Imagine a map of New York City. Instead of solving for traffic flow for the whole city at once, you cut it into the boroughs. Manhattan, Brooklyn, Queens. You give each borough to a different processor on your supercomputer.
Divide and conquer.
Exactly. Each processor solves its own little piece. But the trick is making sure the traffic leaving Brooklyn actually matches the traffic entering Manhattan. The processors have to iterate and talk to each other to agree on what's happening at those boundaries.
And the sources say these two, multi-grid and domain decomposition, can actually work together.
Oh, beautifully. You'll use domain decomposition to split your problem across 10,000 processors, and then inside each of those little domains, that processor runs multi-grid to solve its local piece super efficiently. It's just layers on layers of optimization.
That's amazing. Okay, we've covered a ton of abstract math. Let's bring this home. If someone is sitting there with a massive data set, how do they choose? What's the decision matrix?
It's basically a flowchart. Step 1, look at your matrix. Is it symmetric, positive, definite? If yes, you use conjugate gradient, CG. Done. Don't think twice.
Okay, that's the easy path. What if it's symmetric but indefinite? Has those saddle points?
Then you look at Menarens. It's designed for exactly that case.
Step 3, the big one, non-symmetric. The messy, real world.
This is the most common tough case. And it's a choice based on resources.
Yeah.
If you have plenty of memory, go with GMREs. It's the tank, it's robust, it won't fail you. If you are tight on memory, you have to use BiCG stab. It's jagged, but it's fast and light.
And when do I pull out the specialist, Chebyshev?
You only use Chebyshev if you're on a massive GPU cluster, and that communication is just killing you. It's a niche tool, but incredibly powerful in the right hands.
And probably the most practical advice here, which the sources really emphasize, do not write this code yourself.
Please don't. Writing a good sparse linear solver from scratch is a recipe for pain and suffering. We have libraries that have been optimized for decades. PETS is the gold standard in science. Trilinos is another big one. Even Python SciPy has these built in.
And the key is that you can swap them out at runtime.
Exactly. You write your code once against the library's interface. Then you can just change a command line flag to swap GMREs for BiCG stab and see what works best for your specific problem. It gives you incredible flexibility.
So let's wrap up with the 3 golden rules. What are the big takeaways?
Rule 1, iterate, don't factor. If your problem is big, direct factorization will eat your memory alive. Rule 2, precondition show everything. A solver without a good preconditioner is like a car without wheels. It's not going anywhere fast.
And rule 3,
exploit structure. Don't use a general purpose solver if your matrix is symmetry. You have to match the algorithm to the physics of your problem.
fantastic. Now, before we go, I want to leave everyone with a thought you mentioned earlier. It's a bit of a paradox about the future of computing.
It is. We usually think smarter is better. CG is smart, it adapts. Chebyshev is dumb. It follows a fixed script. But as computers get more and more parallels, we move into the exascale era, the cost of being smart, which requires all that global communication, it's becoming too high.
The smart methods talk too much.
They do. And we're starting to find that the dumber, quieter methods that just compute locally might actually win in the long run. Sometimes, doing less talking is the real key to speed.
Silence is speed. I love that. Something to chew on. Thanks for joining us on this deep dive.
My pleasure. It was fun.
And thank you for listening. We'll catch you on the next deep dive.